Imagine materials all around you, diamonds, table salt, sugar, all solids. But have you ever wondered why they're so different? What makes a diamond so hard and table salt so easily dissolved in water? It all boils down to the arrangement of their atoms in the solid state. So, what exactly is the solid state? In simple terms, it's a state of matter where the atoms, ions, or molecules are tightly packed together. This chapter is super important for your ICSE exams because you can expect direct questions and application-based problems. Plus, it carries a decent weightage, especially when it comes to numerical problems. So, let's get started. Let's start with the first big concept, classification of solids. Solids can be broadly classified into two types, crystalline and amorphous. Crystalline solids have a long-range order, meaning their atoms are arranged in a repeating pattern throughout the entire material. Amorphous solids, on the other hand, have only short-range order. Think of table salt as a crystalline solid and glass as an amorphous solid. Understanding this difference is key. Let's define what a crystalline solid is. It's a solid whose atoms, molecules, or ions are arranged in a highly ordered microscopic structure, forming a crystal lattice. This ordered arrangement is what gives crystalline solids their characteristic sharp melting points. It's like having a perfectly built wall, everything is in its place. Now, let's dive into crystal lattices and unit cells. Imagine building a large structure with identical building blocks. That repeating building block is like a unit cell. A crystal lattice is simply a three-dimensional arrangement of these unit cells. There are different types of unit cells, such as simple cubic, face-centered cubic, FCC, and body-centered cubic, BCC, each with its unique arrangement. Here's a super important formula to remember. Density equals Z times M, divided by a cube times Na. Z represents the number of atoms per unit cell, M is the molar mass, A is the edge length of the unit cell, and Na is Avogadro's number. This formula is crucial for solving density-related problems, so make sure you understand what each variable represents. Let's talk about packing efficiency. This tells us how much space within a unit cell is actually occupied by the atoms. Face-centered cubic, FCC, has the highest packing efficiency at 74%, followed by body-centered cubic, BCC, at 68%, and simple cubic at 52.4%. Remember that higher packing efficiency generally means a denser material. It's like fitting as many items as possible into a box. Here's another important relationship, specifically for face-centered cubic structures. R equals A divided by 2 times the square root of 2. Here, R is the radius of the atom, and A is the edge length of the FCC unit cell. This formula allows you to relate the size of the atom to the dimensions of the unit cell, which is useful in various calculations. Here's a key point to remember for your exams. When calculating the number of atoms per unit cell, be careful about the contributions from atoms located at different positions. Corner atoms contribute 1/8, face center atoms contribute 1/2, and atoms located at the body center contribute fully. This is a common mistake, so pay close attention. Let's work through a quick example. Question: an element crystallizes in a BCC structure. The edge length of its unit cell is 288 picometers. If the density of the element is 7.2 grams per cc, what is its atomic mass? To solve this, first, use the density formula. Second, remember that Z equals 2 for BCC structures. Finally, solve for M, the atomic mass. The answer is approximately 51.8 grams per mole. Let's look at a real-world application, semiconductors. Doping silicon with impurities like phosphorus or boron changes its electrical conductivity. This is the fundamental principle behind transistors and computer chips, making semiconductors absolutely crucial for modern electronics. Here are a few exam tips to keep in mind. First, always draw unit cell diagrams to visualize the arrangement of atoms. Second, pay close attention to units and make sure to convert everything to consistent units before plugging values into formulas. Third, practice as many numerical problems as you can to build confidence and speed. Let's quickly summarize what we've covered. We started with the classification of solids, distinguishing between crystalline and amorphous. Then, we explored crystal lattices and unit cells, understanding their structure and packing efficiency. Finally, we touched on real-world applications like semiconductors. These are the key concepts to remember for your exams. Guess what? All of this, AI-powered notes, doubt-solving support, and practice tests for solid state, is completely free on Synapse. So, ditch the textbooks and study smarter, not harder, with the power of AI. Start your free trial today at synapse.omups.in. Master solid state for ICSE and ace your exams. And don't forget to subscribe to our channel for more free lessons. Visit synapse.omups.in and start learning today.